Hello and welcome to another lecture for my class, PSYC 440-640, the class that's called Experimental Methods, but is really more of a class about univariate statistics. And as you may be able to hear in my voice, I am struggling with a cold. It's been here for about a week, and I think it's getting better, but it's still not gone. And I'll do my best to kind of soldier through this lecture, hopefully speaking clearly so that you can understand what I'm saying, and hopefully what I'm saying makes sense to you and is interesting. I must say, in these moments of physical weakness, I do reflect upon this one comic you can see here from phdcomics.com, which of course uses a graph, which makes it kind of vaguely relevant to a class about statistics, but which really is talking to us about the way we think about our lives, and especially maybe how you think about your life if you're in grad school, this sort of the present moment that you're in and what your outlook is at that point. So if you're in grad school, or if you've been through grad school, you can probably appreciate that. Or if you're kind of struggling for reasons of illness or workload or whatever, maybe you can appreciate it as well. So anyway, this lecture is called Power and Confidence, and it's a title that sounds a bit like the advertising slogan for a men's antiperspirant or deodorant. But it's more than that, and you'll see. What I'm going to try and cover today is a little bit about power analysis, or at least one type of power analysis, with the goal of increasing power. I mentioned in my last lecture that power is a concept that can be quantified, and we can use that concept and use those quantifications in reviewing or evaluating the results of a study that's already been conducted, or in planning a study that we're going to do. Power analysis really has been around for quite a while, but is becoming increasingly, I think, important, or at least the importance of it is becoming increasingly recognized by researchers in psychology and the behavioral sciences. So I'll try and give you a bit of a primer on that. And then time-dependent and sickness-dependent, I'll talk a little bit about confidence intervals. Confidence intervals are, well, you've almost certainly seen them before. You've seen error bars on graphs, which are sometimes based on confidence intervals. And so you probably have a sense of what they are or what they mean, but it's worth spending a bit more time with them. And I didn't really have a good place to put them in a previous lecture, so I'm just going to kind of put them here. And hopefully the transition from the one topic to the other won't seem too abrupt. Anyway, where we left off last time, I had given a lecture that I just called Statistical Decisions, or Making Statistical Decisions. Really what it was just kind of an introduction to null hypothesis significance testing, which is, broadly speaking, this approach that we use often in research, especially in psychology and the behavioral sciences, to evaluate claims that we make, to test hypotheses that we make. And if we want to get a little bit historical about this, it's actually an amalgamation of two approaches. One was developed by R.A. Fisher, this founding figure in the history of the types of statistics that we often use in psychology, and he developed an idea called significance testing, and gave us this idea of an alpha level, the 0.05 that we're familiar with, which he actually picked somewhat arbitrarily, and so he kind of advanced that idea and developed some of the computational techniques to make it easy to use for applied statisticians and researchers. After that, Egon Pearson, who's the son of Carl Pearson, one of Fisher's intellectual rivals, I guess you could say, Egon Pearson and Jerzy Neyman, two other statisticians, later kind of developed the idea of hypothesis testing, which introduced the concept of a null hypothesis and an alternate hypothesis. And for what it's worth, Fisher and the younger Pearson and Neyman camps kind of argued back and forth for a long period of time, and sort of professionally and maybe even personally disliked one another over their disagreements as to whether significance testing was the more appropriate approach to testing hypotheses, or this so-called hypothesis testing approach is more appropriate. What's interesting, though, is that folks who work in research and who aren't themselves statisticians, in a sense, kind of just combined both methods, have squished them awkwardly together into this term that we now have, null hypothesis significance testing, which in a way combines elements of old school significance testing and the somewhat more recent innovations of hypothesis testing. And if you've spent any amount of time on the internet, reading blogs about research methods or following Twitter feeds about psychology, you've probably seen criticism of null hypothesis significance testing. This criticism is current and ongoing, but it's really not new. Researchers in psychology and in other fields, people like Lee Cronbach and Jacob Cohen and Paul Meehl and others were complaining about not so much null hypothesis significance testing, but the way that researchers tend to misuse this approach as far back as the early 60s at least. And they then, and people now, blame null hypothesis significance testing for some of the slow progress that we make as a field in psychology, some of what we now call the replicability crisis, where apparently well-established effects and findings don't seem as robust as we thought. Some folks put that down to the misuse or just the use, full stop, of null hypothesis significance testing. I'm not sure I'm entirely on board with all of that criticism, although I will clearly acknowledge that NHST can be really misused and often is by researchers. But I will say right now, I think it's important to understand how null hypothesis significance testing works, because it's been around for a while and it's kind of the engine that drives the analyses of most of the papers you're going to read in research in psychology and other sciences that are related. And it'll probably be around for a while longer. There are other approaches to hypothesis testing. There's graphical representations of data. There are certain techniques that are sometimes called exploratory data analysis. There are approaches to simulations for data sets, which can be used to evaluate hypothesis. Bayesian statistics are an entire branch of kind of probability theory and applied probability theory that attempt, well, that can be used under some circumstances to test hypotheses. So there are alternatives out there, and it seems like every few years someone writes a big paper or a famous blog and says, okay, we should throw away NHST and we should all just become Bayesians, or we should all just do, sort of Monte Carlo based simulation analysis or something like that. And maybe one day we will, but in the time between now and then, I think it's important to understand how to do NHST right. And part of that involves power. So that's kind of the hook or the connection here. Anyway, if we want to simplify some of the complexities of NHST, we can think about it kind of like a process. And the process, once we've developed some hypotheses and gathered some data and are actually sitting down looking at our data in our data set, the process begins with calculating some sort of a test statistic, which represents, for instance, the comparison between two groups that we have in our study, or the comparison of a value for a correlation against some other value that we think the correlation might hold. What we do is we discover, in a sense, the probability of that test statistic in a sampling distribution under the null hypothesis. So we ask, if it is the case in the population of all data that there is no such effect or no such relationship between whatever our predictor variable is and whatever our outcome variable is, how probable is it that we would find the test statistic which we have in fact in this data set found? Then we compare that probability to some criterion, and for reasons that have a lot to do with history and not much more than history, that criterion in psychology is 0.05. Again, somewhere I have a paper around my cluttered office that talks about the history of why Fisher chose 0.05 as his level for alpha, and the last time I read the paper, it was sort of like he just kind of picked that value, 1 in 20 chance, and that seemed to stick for most researchers ever since. So anyway, we compare the probability of our test statistic, the probability of the t statistic we just computed, or the f statistic, or the chi-square, or whatever, to some arbitrary probability value like 0.05, and then we make a decision, and that decision is to reject or to fail to reject the null hypothesis. Now, if you've taken other stats classes, you'll have detected I sort of skipped over maybe a step that should be earlier in this process, where we begin by assuming the null hypothesis. And what that means is we just begin, or we take as our starting point the idea that in the population there is no effect or no relationship between predictor and outcome, or no correlation, or whatever it is we're studying. And we don't prove that, or we don't demonstrate demonstrate that that is true, we just begin with that as an assumption, and that assumption can be retained if we fail to reject the null hypothesis, or it can be rejected. That's kind of the decision-making process in the statistical decisions, at least when we're doing NHST. Now, one of the problems, or one of the criticisms that's often made of NHST is that when researchers do it, they often focus too much or even exclusively on one type of error. If you think back to the last lecture, hopefully you'll remember that there are different types of errors you can make. You could, for instance, reject the null hypothesis when the evidence to reject it is, or when you shouldn't, so claiming to find an effect based on your sample data when in the population no such effect exists. You made a type 1 error or a false positive, or you could make a type 2 error. You could fail to reject the null hypothesis based on your sample of data when in fact in the population there is some difference or effect or whatever between the predictor and outcome variables. In that case, you've made a false negative or a type 2 error. So there are two types of errors. Actually, statisticians have come up with other ways of thinking about the mistakes you can make in research, but for the time being, let's just say there are two types of errors. And researchers often focus almost obsessively on the type 1 error, the alpha level of 0.05, and they sort of very quickly orient themselves to the output from SPSS or Excel and see, oh, is P less than 0.05? If it is, great, I can reject the null hypothesis and publish my paper and get famous. And if it isn't, they think, boo, I can't, I'm stuck. What we should be considering is more information here when we make statistical decisions, or if we want to use NHST the right way. We should be thinking about the different types of errors we can make, at least the false positive and false negative, or type 1 and type 2 errors. We should also be thinking about the magnitude of the effect we've observed, and we should also be thinking about the power we have to detect such an effect in the population. And that's important, and that's essentially power analysis. So just to quickly review those concepts that I just mentioned, and this is if you haven't seen, pardon me, if you haven't seen the last lecture in a while, or if you need a refresher, type 1 error rate, or what we sometimes call alpha, is our likelihood of making false positive mistakes, false positive errors. Type 2 error, or beta, which I always find a bit confusing because in the world of regression there are other things we call beta, is the false negative, or is the probability of making a false negative error. And whereas we typically stick with this criterion, albeit a somewhat arbitrary criterion of 0.05 for alpha, there is no, by tradition, fixed criterion for type 2 errors. Maybe this is because historically researchers have been less concerned about making type 2 errors than they have been about making type 1 errors. That said, researchers and statisticians who think about this stuff, particularly Jacob Cohen here I'm thinking of, have argued that we should have at most a type 2 error rate of about 0.20. We ideally could have a lower type 2 error rate, but as you'll see, there's often, at least for a fixed effect size and fixed sample size, a trade-off between our type 1 error rate and our type 2 error rate. All right, so that's type 1 and type 2 error, our two types of error, at least for the purpose of this lecture. Now we have effect size, and effect size, as I mentioned last time, are just any of a number of different standardized ways of quantifying the magnitude of an effect we're studying, the size of the effect, of course. Now, when I say effect, I could be talking about a difference between two groups in a population, comparing a treatment group to a control group, or I could be talking about the strength or the magnitude of a correlation between a predictor, between two variables, or I could be talking about the magnitude of the unstandardized regression coefficient that we use to predict an outcome variable from a predictor variable, or I could be talking about a lot of other different things. Those are the effects, and often it's useful to represent those effects in a kind of a standardized way that can allow us to compare across different studies or even different parts of one study the magnitude of one effect versus the magnitude of another effect. And so there are lots of them out there. The ones that I like the most are the ones that are most directly based on correlation. This humble Pearson product moment correlation, R, is itself an effect size. Others that are familiar have to do with group comparisons, like Cohen's D, which you might use if you were running a t-test. There are others out there. But the point is, in some way, regardless of what effect size measure we use, we should be thinking about the magnitude of the effect that we're trying to examine. And now the fourth, or third, I guess, on how you're counting these things, thing we need to think about is power. And this is the likelihood of correctly detecting an effect. That is, the likelihood of not making a type 2 error, of rejecting the null hypothesis based on the data in your sample when there is an effect in the population. There is a difference between the two groups, or a correlation between the two variables, or so on. And because power is literally the likelihood of not making a type 2 error, it's very easy to calculate. It's just 1 minus whatever beta is. Power, may be sort of easy to grasp or easy to think about, but it might not. It depends on how sort of statistical your mind is. If you struggle to think about power, the metaphor that sometimes is helpful maybe is of sort of the ability of the radar detector or the radar operator to detect incoming airplanes. If this is a military radar operator and he or she is looking for incoming enemy aircraft, or if it's an air traffic controller at an airport, his ability to kind of detect an incoming plane, detect a plane that is really out there in the population, that is in the sky, based on a sample of data he has, that is the radio waves that are bouncing back to him and being received by his receiver. So in other classes, I use this metaphor more, and for some people it really clicks, I suppose. So maybe that's just a suggestion for right now. So however you choose to think about it, power is important. And in fact, power, as you would guess from the name, is a thing that we spend a lot of time with when we do power analysis. So to put this all together, we shouldn't really focus on alpha, at least not entirely. We should also consider beta, power, and effect size. We should consider all the relationships between these different qualities when we're doing a set of analyses. And power analysis is really just that. It's a way, or really a set of different ways to examine the relationships between these two types of errors and power and effect size. So with that in mind, let's do some really basic power analysis. For the purpose of this lecture, imagine a research scenario. You're a psychophysiologist and you're studying the effects of alcohol on fear response. And this example, for what it's worth, comes from my own experience of doing my master's thesis many, many years ago in graduate school. Imagine that you are doing an independent experimental design. So you're bringing people into the laboratory, you're assigning them to be in one group or another group. Those groups don't overlap in terms of the people who go into them, so they're independent. Your independent variable or predictor variable is a dose of alcohol. So the one group of people is given a standardized dose or a calibrated dose based on their height and weight or something. They're given alcohol to drink, and let's presume they become intoxicated. The other group is given none. They're either given nothing to drink, or maybe they're given not an alcoholic beverage with their knowledge, or maybe they're given a placebo where they're told that they're drinking alcohol, but they're really not. We have some sort of a counterfactual that's set up here in our no alcohol group. And then our dependent variable is a measure of psychophysiological response that's associated with fear. That is the eye blink component of the startle. So if all of us, I think, have had the experience of being startled by a sudden sound, someone bangs, a door behind you and you jump, that jump occurs across a lot of different muscle systems in your body. And you might know that the blink is one of the most reliable and consistent elements of that overall body response. Humans and lots of other animals that blink, when you startle them. And so you can startle someone by putting headphones on them and intermittently introducing noise blasts, like, in their ear, which will make them blink. And you can measure the latency and the amplitude of that blink response in terms of electromyography or EMG. And for reasons that have to do with the neural circuit that guides that response, you can make some inferences about the activity of different fear centers in the brain, particularly the central nucleus of the amygdala. So again, imagine you're doing this study because you have this theory that alcohol makes people fearless. That theory seems to explain why people do dumb stuff when they're drunk. You want to test it experimentally. So you're doing the experiment, you're manipulating people's level of intoxication from alcohol, and you're measuring their level of fear response, which is operationalized here psychophysiologically as the eye blink startle. So that's a lot of me talking, but if you want to represent this pictographically, you could just use our old and now probably rather familiar, even to the point of being generic, example of a simple independent experimental design. We've got alcohol and no alcohol, and we're looking to see if there's a difference in eye blink startle reflex. And as I note here in my little call-out box at the bottom, let's hope that people are randomly assigned to group, because if they're not, there are potentially all sorts of problems with confounding variables that could occur. So probably there should be a little arrow or note indicating that people are randomly assigned. So again, we're studying the effect of alcohol and fear response, and for the purpose of this example, let's assume we have a really small sample, a ridiculously small sample, only 10 people, so 5 people per group. That's just way, way, way too small. But I chose this deliberately, and you'll see why by the end of the lecture, hopefully. We're starting with a small sample. Now, if you can imagine, if you did this study, your analyses might be very simple. You might just do an independent t-test to compare the amplitude, let's say the mean startle amplitude in the alcohol group to the mean startle amplitude in the no alcohol group. Or you might do 2 t-tests, one for startle amplitude and one for startle latency. But bottom line is, it's a pretty simple analysis that you'd be doing. What is the power in that analysis, or what was the likelihood in that analysis that you could detect a significant effect in the population? Well, we can use G-Power, which is a free piece of software, which I talk about a lot in class, and which I've mentioned, I think, way back at the beginning of this series of video lectures, to do a post hoc power analysis. Post hoc power analysis just means that we are looking at the sort of observed power or attained power, or I should say achieved power of a set of analyses that have already been done. So if you open up G-Power, you'll get a screen that looks something like this. Every few years they kind of update and tweak it a little bit. You can select the family of tests you're doing. It happens to be t-tests. You can select the type of test that you're doing. Well, it's a difference of means between 2 independent groups. That's the analysis you did. And then you can select the type of power analysis. There are some different options. Again, we're doing what's called a post hoc power analysis now. Once you've selected all those different options, you have what G-Power calls a set of input parameters. These are just the settings that you give to G-Power to tell it the type of analysis you did. Now, for the purpose of this example, we're going to do one-tailed t-tests. That's mostly because they're a little bit easier to visualize in terms of the graphic output that we get from G-Power. And maybe we might begin with this sort of hypothesis that alcohol can only decrease people's fear response. So maybe we can justify doing a one-tailed test to compare the alcohol group to the no alcohol group. That's iffy, but let's imagine that's how we roll. So we select a one-tailed t-test, and let's say our effect size is small. For a t-test, the most common effect size is Cohen's d, so that's what the input parameter asks for here. And you might know off the top of your head that Cohen's d of 0.2 is generally considered a small effect, or that's the size of Cohen's d that corresponds to generally small effects. If you didn't know that, you could look at that up online or in most stats textbooks, or if you click that determine button, you would have a couple different little options that would pop up to allow you to make a guess at your effect size. Or if you hover your cursor over the field, you'll get, I think, or at least in my version of G-Power, you get a little pop-out box that gives you a suggestion of what a small, medium, and large effect size is. So to be clear, had we done this study for real, we could know the effect size that we saw in our sample data. We could compute Cohen's d for our sample. But for the purpose of this example, just because it's made up by me right now, let's imagine that we observed an effect size of 0.2, a small effect size. Okay, moving on, our alpha error probability, that's our type 1 error probability. That's the familiar 0.05. You don't need to, that's probably set as a default, but if it isn't, you type in 0.05. And then the sample size for group 1 and group 2, there are only 2 groups in a t-test. There are only 10 people in our study, so obviously that's going to be 5 in each place. So once you've hit all those, or set all those input parameters, you hit calculate, and you'll see the numbers on the kind of right side pop up, and you'll notice that power, 1 minus the type 2 error rate, is about 0.09. So we have about a 9% chance of detecting an effect, assuming that there is a small effect in the population. Now, at this moment, if this is a real study, you could imagine you or whoever the researcher is who's doing it saying like, well, that's not a lot of power. That's clearly a low likelihood of detecting a significant effect, but maybe I did detect a significant effect in my sample, therefore I must have had enough power to detect an effect. This sort of somewhat flawed thinking is pretty common in psychology, and I actually address it a little bit in a supplemental video, which, and so for that reason I won't get into it now, but if you're interested in power analysis, or even if you aren't, I encourage you to watch that supplemental video because it kind of picks up on that. What I see is a kind of a flaw in people's thinking about how power works. But we won't go into too much of that right now. Instead, let's just focus on the idea of increasing power. Everyone would agree that less than 10% chance of detecting an effect in the population is not enough power. And as you probably know from my lectures, or maybe you just know this from your own studies, people have criticized psychology and other sciences as well for tending to run low power studies. So you might well wonder, we didn't have a lot of power in this study. Let's say we're going to try and replicate it. We need more power. How can we do that? Well, there are some different options. When I ask this question in class, almost invariably the students will chime in and say, well, you can increase sample size. That'll increase power. That's true, or it's almost always true. So that's one option. There are some other options as well, though. We could increase alpha. We could make the type 1 error rate greater than our typical 0.05 type 1 error rate. That would also influence power. We could reduce error, and by that I mean reduce the error in our data, and I'll talk about some ways that we can do that. And we can increase the effect size. That is, we can do things, often sort of design-wise and methodologically, to have a bigger effect, because as we'll see, and as you might intuitively understand, big effects are easier to detect than small effects. We have more power to detect them. So different options. It's not just increasing sample size. And maybe if you go no further in this lecture, that's maybe enough of a take-home point. Sometimes when people say, oh, we need more power, just get a bigger sample size. Well, that's not a bad thought, but there's often more you can do. And with that in mind, I want to first focus on this idea of reducing error. I'll go through all of these, but first I want to focus on reducing error. Now, by reducing error, what I mean is we want to have a situation in which the data in our data set, that we've gathered, is cleaner. It is less variable in an unsystematic way. So one thing we can do is we can try to get better data. We can, if we're replicating our study, we can improve our design and our methods so that there is less measurement error. So perhaps in the case of our psychophysiological study, you can think about our outcome variable is, eye blink startle, which is, its magnitude and latency are measured using software. Perhaps we can check with the company that makes the software and see if they have any updates, and perhaps they do, or perhaps there are settings within that psychophysiological equipment that can give us a higher sampling rate or better resolution, in terms of how big the startle is. I mean, there are all sorts of little things that you would fiddle with to get the most sensitive measure of eye blink possible. And even if you're not a psychophysiologist, I think you can appreciate that a more finely tuned measurement device, in this case, all the amplifiers and filters and digitizers that you need to do psychophys, more finely tuned equipment will give you better measurements than really poorly tuned equipment. That's one thing that would at least in principle, improve our data. We could also think about improving our research design. Imagine that in our design we have people in this or alcohol group and this no alcohol group. The alcohol group, they just drink a standard dose of alcohol. They all get the same amount of alcohol. Now, that may seem like a good idea, and perhaps in some ways it is, but you could imagine if you had people in that alcohol group who varied in terms of their gender, who varied in terms of their height and weight, or just kind of overall body size. The people who are smaller or female, and females tend to be smaller and for other reasons tend to be more affected by alcohol, might get drunker than the people who are bigger and male. That kind of standard dose of alcohol could introduce something like a confound where people in that alcohol group aren't all comparably drunk. Some people are really drunk. Some people are not very drunk at all. You might improve your design by replacing that one standard dose of alcohol with a calibrated dose. There are various regression equations that you can use and dosing protocols that have been developed by pharmacologists over the years to try and guesstimate how much alcohol you have to give a particular person to get him or her drunk to a certain level. And you could use one of these and end up in a situation where you had a more standard level of intoxication once people were done consuming however much drink they consumed. That would mean, hopefully, that the level or the effect that alcohol has on fear response would be more consistent. Instead of having an inconsistent effect on fear response, when some people are really drunk and some people are not very drunk, you have a more consistent effect. The point is, by tweaking our design and our methods, I just gave some examples here, we could have data that has less measurement error in it. And that's important because measurement error, at least unsystematic measurement error, by definition can't correlate with anything. It's like a static or noise, to use that signal and noise metaphor, that gets in the way of us or that obscures our ability to detect an effect. So sometimes people doing research overlook this step. I would argue that one thing you can do is improve your design, improve your methods with the idea of getting better quality data that will probably help you down the line in terms of giving you more power to detect effects. Another way to reduce error, and I've talked about this a little bit before, is to have a better model, to have a better way of predicting variability in that outcome variable. So you can imagine adding more variables to improve prediction. We have a regression equation that looks a little bit like this, and what we can do is take variables which exist in the error term, the little e, and move them into the main part of the model, move them in as predictor variables. Kind of essentially taking what would be confound variables lurking ghost-like in the error term and bringing them into the house, into the room, into the model. So if that seems a bit abstract or hard to follow, consider that we're trying to predict people's level of fear response. And in the design that or the scenario I laid out for you, we have one predictor variable, which is just whether you drink or whether you don't drink. And that's not bad. That's a very simple model, and hopefully there's some relationship there. If not, then maybe we've wasted our time. But there may be other things that influence people's level of fear response. For instance, personality variables like trait neuroticism might influence how jumpy you are. Or there may be other kind of psychological variables, and neuroticism seems like the obvious one to me. Level of trait-wise anxiousness, which is probably more or less the same thing as neuroticism, might influence how jumpy people are in terms of their psychophysiology. Now you could imagine revising the model so that you don't just predict people's level of fear response based on their level of intoxication, drunk or sober, but also based on their level of neuroticism, high or low, or some sort of continuous measure of neuroticism. Now that type of study is slightly different, and of course that presumes that you could use some sort of a questionnaire to measure people's level of neuroticism. Perhaps before they participate in the main part of the study, you have them fill out a questionnaire. And the nature of the study is now somewhat different because we're no longer looking at just alcohol. We're considering two variables, and maybe even down the line whether those two variables interact. But in any case, we've made a potentially better model, a model which makes less error in terms of predicting people's level of fear response, their level of psychophysiological sort of startle, magnitude or latency or whatever it is we're looking at. Better prediction, less unsystematic error in prediction, less noise, less static in the signal, obscuring our ability to detect an effect. So if you're struggling with this a little bit, or I guess even if you're not, let's consider an example. Imagine you're an experimental psychologist studying self-control. Seems like self-control is one of those perennial topics in psychology, going back at least as far as Freud and continuing even to these days. Let's imagine you're doing an independent experimental design and you have a predictor variable or an independent variable that's called ego depletion. And if you've read, again, anything in terms of the recent writing and blogging about psychology, you know that ego depletion was or still is this construct that at least some people in experimental social psychology are very interested in. It reflects the idea that when you do a task that's hard or maybe even impossible, you kind of run out or run down a reserve of energy of some sort that you have, and because you're kind of depleted, as the researchers would say, if you then have to do some sort of other task that's hard, or you have to withhold a behavior that you might be tempted to do, you have less ability to withhold. It's like, I think the subjective experience many of us have, and why ego depletion seems like it kind of makes sense, is that probably all of us have had the experience of wanting to watch what we eat, wanting to not eat a lot of junk food. And maybe one day you come home from work and it was a pretty easy day of work, so it's very easy to sit down on the couch and eat some fruits and vegetables, like have some baby carrots or an apple, because yeah, you're tempted to eat junk food, but you can resist that temptation. Maybe the next day you come home from work and it was a really terrible day at work and you were just all day long frustrated and angry and tired, and now you sit down to eat your snack, watch television or whatever, and it's harder to resist the pull of eating potato chips or chocolate chip cookies or whatever it is. That's a feeling or an experience I think most of us have had, and I think in some sense that's the idea that these researchers are going at when they look at this depletion idea. So anyway, imagine you have an experimental design. People are brought into the study. They're randomly assigned to one group or the other. One group is just a control group. They just hang out for 10 minutes, let's say. The other group's the depletion group. They're given some challenging or frustrating task. Maybe they have to solve anagrams that are very hard, or maybe even have no solution. And so they get kind of depleted over the 10 minutes that it takes them to struggle with that. Your outcome variable is then some sort of measure of self-control. Maybe it's like a cue, that pops up on a computer screen. It's a picture of a cupcake, or maybe even you bring in a plate of cupcakes or cookies into the office and say, all right, you really shouldn't eat these because they're for some other folks coming in, but I'm not going to watch, or I'm not going to babysit you, and you walk away. And people have to either, you measure how much people say they want to eat the cookies, or maybe you observe surreptitiously if people do cheat and eat the cookies, and that's your outcome variable, how much they cave in to temptation. All right. I should say, in this example, let's imagine that you use a simple questionnaire, like a single item measure, like how much can you resist these cupcakes? That's your only outcome measure for your outcome variable. So imagine that we ran this study, but then for whatever reason we wanted to replicate it. We wanted to do it again, but do it better with more power. How could we maybe adjust the methods that we use to get better data with less error? Well, one thing we could do to reduce measurement error would be to use some sort of a multi-item scale. Instead of asking people on a single item, how much temptation do you have to eat this cupcake? We could use a multi-item scale which asks multiple questions related to urge or temptation, or gives us a kind of a more robust estimate of how much craving the person feels. There are, I remember this from years ago in grad school, there are rather sophisticated ways of thinking about craving for alcohol, craving for drugs, craving for junk food. And we could try and choose one of these existence scales rather than just using our own rinky-dink one-item measure. Ideally, this is something, we choose a measure that has been validated as a good measure of craving. Maybe something specifically that's a good measure of craving for junk food like cupcakes. I don't know. The point is, if we replicated our study, if we repeated it, but used better measures, better methods, we'd probably end up with less measurement error. We'd have, in a sense, better data, and we'd have more power to detect effects that are there. If we wanted to increase our power, we could also reduce our error in estimation. And that's that second way of thinking about reducing error. That's like changing our model so that the model does a better job predicting the outcome variable. So for instance, instead of using just depletion group, were you in the frustrated depletion group or were you in the control group, we could add other predictor variables which might plausibly be related to how much temptation people feel towards eating cupcakes. Things like the amount of time or the amount of hunger that they feel just in general. Are you just a hungry person or not? Or the amount of time since their last meal. Someone who just had a filling lunch before rolling into the laboratory might not feel a ton of temptation to eat a cupcake. If we included those variables, we would probably do a better job at predicting people's level of craving. There'd be less error in our prediction. It'd be easier to detect effects in our when we do hypothesis testing for our model. By the way, you see in this little pull-out box here, these kind of ideas of statistical control and experimental, or maybe a better term would be methodological control. In research, I know I've talked about this before, and I'll probably talk about it again. We often talk about control, and what we mean is reducing or constraining the effects of confounding variables on relationships between predictor variables and outcome variables that we're interested in. We can achieve, or we can try and achieve at least, control in different ways. One way is experimental or methodological, where we adjust how we run our study or how we gather our data to reduce error. So for instance, let's say we are really worried about time since last meal as being a confounding variable. We could experimentally or methodologically say, look, you can only come into this study if it's been 4 and no more, no less hours since your last meal. Or we could enforce like a fast. You sign up for the study in the morning and you come in 3 hours later, 4 hours later. If that worked, and if people followed our instructions, then everyone in our study would have the same level of time since last meal. We would have experimentally or methodologically controlled that confounding variable, and we could ignore it because everyone's the same on it. We might imagine that maybe men and women differ in terms of their feelings about cupcakes. I don't know, it sounds a bit sexist, but let's imagine that women like cupcakes more than men. We could only recruit women for our study or only recruit men for our study. That would control experimentally, methodologically, the variable gender, which might otherwise obscure or confound the relationship that we're looking at between predictor variable ego depletion and outcome variable craving. Or we could, take those same variables, time since last meal or in gender, and we could not experimentally control them, but we could statistically control for them. We could measure time since last meal when people come into our lab, or we could measure or ask people to self-report their gender. And that would give us those variables, which we could then enter into our model, and we could use those either as independent predictors or see if they interact with our main predictor variable, ego depletion, and so on. That would be an example of statistical control. We could say, holding the effect of time since last meal constant statistically, there is a significant relationship between ego depletion and craving. That would be statistical control. So either way, one approach to increasing power is to reduce error. The important idea here is that unsystematic error, this thing I've talked about a few times now, is just variation in our outcome variable that isn't associated with variation in the predictor variables that are in the model right now. That's the very definition of unsystematic, right? It's variability in how much craving people have, or variability in how much psychophysiological response people have that doesn't connect to the predictor variable that we're interested in. That's why we sometimes call unsystematic error random error, because it doesn't seem to be related to any variables that we currently are considering. So if we want to get a little bit more technical about it, we can note the unsystematic error tends to increase the denominator of the calculations that we do for test statistics. So if you look at the bottom of the slide here, you can see a formula for the t-statistic calculation for an independent samples t-test, assuming both groups have the same sample size. And the term that you see in the bottom, S sub p, is the pooled standard deviation for the two groups in our sample. As that value gets bigger, as the data becomes more variable, some people have very high scores, some people have very low scores, in a way that isn't associated with treatment group or our predictor variable, then that value gets bigger, the calculation of test statistic gets smaller. The value of the t that we compute has to get smaller when that denominator gets bigger. And small values for test statistics are found more frequently in null sampling distributions than they are in large values for test statistics. So it becomes harder to reject p less than 0.05. It's harder for us to reject the null hypothesis if we have a lot of error that we're measuring. So at the risk of digressing even further on this point, I'll just note that the sources of unsystematic variation in our data for our outcome variable are variables themselves, and we sometimes think of them as confounds. We can deal with unsystematic variation by equating all participants on those variables. So in my example before, enforcing some sort of a fast to experimentally or methodologically equate all participants on a potential confounding variable of time since last meal. Or we could imagine a different sort of study where gender, for whatever reason, is a confound. So we're only recruiting men or we're only recruiting women, to equate all participants in our sample on that variable. Doing so would create a situation in which there was no variation in these confounding variables, so there's no possible covariation with our outcome variable. And unless it's, in case it isn't already clear, those examples, or in the way I've described it, would be examples of experimental or methodological control. We can also think of these unsystematic, these sources of unsystematic variation as variables which are not in our model yet, meaning our augmented model. Now we can deal with unsystematic variation by adding these variables to our model, using them as predictor variables to see whether or not they independently predict our outcome variable, or if they interact perhaps with our main predictor variable or variables in predicting our outcome variable. These would be examples of statistical control. So for instance, we could, in the example of our ego depletion and cupcake eating study, we could measure people's level of hunger when they walk through the door and use that in our model and explore its relationship to the outcome variable. Or we could try to covary for that. We'll talk about statistical control and covariance later on in this unit and in the following unit. These would all be examples of statistical control for sources of for sources of unsystematic variation or unsystematic error. So okay, just to tie it all together here, let's say that the really important point is that reducing error makes it easier to detect effects. That is, the effects that we're interested in. That is, relationships between our predictor and our outcome variables. Doing this increases our power, which is one of the reasons why we might want to spend a lot of time thinking about our methods, thinking about our study design, so as to reduce sources of unsystematic variation, to increase power, give ourselves an easier chance of finding an effect, that is, a relationship between our predictor and our outcome variable, if such an effect exists. Okay, let's get back to our example of alcohol and the fear response as operationalized by eye blink startle reflex. So we want to increase power, and we've already talked about one of our options. That would be to reduce error. Let's move on and talk about another option, and that would be to increase the type 1 error rate. So how might this work? We want to increase type 1 error rate, and that helps us because type 1 error rate and type 2 error rate are linked for a given effect size and sample size. Specifically, they're inverses of one another. So if we increase the type 1 error rate, we decrease the type 2 error rate, and this increases our power, since power is 1 minus type 2 error rate. If we flip it around, if we decrease type 1 error rate, we increase type 2 error rate and thereby decrease power. to see how this works, let's look at a graph in G-power. Let's begin, as we often do, by assuming that the null hypothesis is true, that there is no effect in the population. So we might represent that with these two sampling distributions here superimposed over one another. There's the null distribution and the alternate distribution kind of located in the same place on our number line. We'll see in future examples what this looks like when there is an effect and those two sampling distributions start to separate. But anyway, we're beginning, we've got this ridiculously small sample of people in our study, and we've got a particular test statistic that is a critical value for our sampling distribution under the null. It happens to be about 1.86. Now that value is just the value which gives us a line that kind of divides the sampling distribution under the null hypothesis into two regions. One region that includes 95% of all the values for the test statistic that can occur under the null distribution, and the other region which is just the remaining 5%. By the way, I'm saying two regions here because for this example and for all the previous or all the following examples, I'm going to use one-tailed tests of significance, and that's mostly just because it's a little bit easier to visualize. The graphs get kind of cluttered with all my arrows and boxes otherwise. So anyway, this is our critical value, and it's the critical value that is associated with our type 1 error rate of 5%. So if we had a different type 1 error rate of like 0.01, 1%, we'd have a different critical value, a much bigger critical value. Again, the point is that's the value in our sampling distribution under our null hypothesis that we need to beat with the test statistic that we calculate in our sample of data. So to be clear, if we had a sample of data and we calculated a test statistic of t equals 2.0, that value is greater than our critical value of 1.6. That value, 2.0, occurs in the sampling distribution under the null hypothesis, but it occurs less than 5% of the time, and we reason that that gives us the ability to reject the null hypothesis. It would be unusual to find a test statistic of the size that we have found in our sample if in fact the null distribution was a good description of the data in the population. Okay, so this is the main workspace for G-power. If you've downloaded and opened up the program, you're probably looking at something that looks a little bit like this. And just to orient us, observe that there's a pull-down menu for test family. You can kind of see that over on the left there. Because in this particular example, we are using a t-test to look at the difference between the group who consumed alcohol and the group who did not consume alcohol, I'm of course going to select t-tests. Now the specific type of t-test I'm doing is an independent t-test because I'm looking at differences in the means of two groups that do not contain any of the same people or same cases. So I'm selecting the type of statistical test here in that big pull down menu for means, difference between two independent means, parenthetical, two groups, pretty straightforward. The type of power analysis. There are different types of power analysis we can do, but in the examples I'm working through right now, we're treating these like post hoc power analyses, imagining that we've already done the study and we maybe have observed an effect that we think is statistically significant, maybe we haven't. We're just trying to get a sense of how much power we have given our level of type 1 error rate, our sample size, and the effect size that we've observed. So long story short, I'm selecting post hoc. There are some different options, and if you play around with G-power, you can get a sense of the different options you get. Post hoc is going to work for us right now. Now, for the input parameters for this analysis, it's probably the case that the tails of the test are set to a default of two-tailed tests because that's most common in psychology and a lot of other behavioral sciences research. In this case here, largely for the purpose of visualization, I'm just going to select one-tailed test. Maybe this makes sense because maybe I have a strong theory which gives me a very good directional hypothesis that people who consume alcohol will have lower levels of startle reactivity than people who do not. But again, for the purposes of this lecture, I'm mostly doing it just for the visuals. So that's set for one tail. Determining effect size. Effect size here is given by Cohen's d, which is pretty common when we're doing t-tests to compare different means from different groups. If you hover your cursor over the field for where you can type in numbers, you'll get a little pop-up guide which will give you suggestions for what constitutes a small, a medium, or a large effect size in terms of Cohen's d. You can also click the button to determine to get some options for determining what the effect size is in your data. So to be clear, if you had really gathered the data for your study, you would calculate the observed effect size that you have based on your sample of data, and that effect size is essentially an estimate of what we think the effect might be in the full population of data. For right now, I'm just going to enter 0.2 because I'm imagining in this example that I have observed a small effect, and 0.2 Cohen's d is a small effect by sort of tradition. My type 1 error rate is 0.05. That's our standard level of type 1 error rate for most research in psychology. And the sample size for group 1 and group 2, it's 5 cases, or 5 people in each group. So those are the basic input parameters. Imagine that you've dialed all those in, or if you're playing along with me on your computer, please do go ahead and dial all those in, then click the button that says calculate. Okay, so once you click calculate, G-Power will give you a graph that looks a little bit like this. Again, we've got our ridiculously small sample of people here, and we can now see the two sampling distributions somewhat separated from one another. We have our red line giving us our sampling distribution for the test statistic under the null hypothesis. That's the probabilities of all the values of the test statistic that we would observe if in the population there is no difference between these two groups. It's in red there. And in the dotted blue line, kind of in the back or in the front, depending on how you squint your eyes, is the sampling distribution. It's for all the probabilities of all the test statistic values we'd observe under the alternate hypothesis. The alternate hypothesis that's specifically defined by our effect size. You can think of the effect size as literally the amount of space on the number line, or the distance on the number line, that separates the null sampling distribution from the alternate sampling distribution. In this case, that distance is pretty small because we have a small effect, and you can kind of see, I think pretty obviously, that the alternate sampling distribution is only sort of pushed ever so slightly to the right of the null sampling distribution. You can see here our critical value for our test statistic. That's the same as it was before because we're still, for the moment at least, using our type 1 error rate of 0.05. So that critical value of about 1.86 divides the null sampling distribution into two regions, one associated with 95% of the values, that's to the left, and the other shaded in red to the right is our 5% region. That's our type 1 error rate. And you can see here that the critical value also divides the alternate sampling distribution into two regions. One region to the left of the critical value in the alternate distribution, and shaded in blue here, is the area associated with the type 2 error rate. So imagine that the alternate distribution is, the alternate hypothesis is true, that there really is in the population of all possible data a difference between people who drink alcohol and people who don't drink alcohol in terms of their eye blink reactivity. If we got a test statistic that was less than 1.86, let's just say it's 1.00, then we would fail to reject the null hypothesis. That would be a mistake, a false negative, a miss, if in fact there really is a difference in the population. And the probability of us making such a false negative mistake or such a mistake is given to us by that shaded blue region in the alternate distribution. And we can know, or we can look up the amount of space that is. The cumulative probability is about 0.91, and power is 1 minus the type 2 error rate, so that is 0.09. That's the area under the dotted blue curve in the alternate distribution to the right of the critical value. So less than 10% power to detect an effect. We observed in our sample a small effect. Perhaps we rejected the null hypothesis, but we had about 10%, if we want to be really generous with ourselves, power to detect an effect because the effect is so small and our sample is so small. So the whole point here is that we're trying to see how fiddling with the type 1 error rate could change this outcome, or change this analysis, I should say. So let's go ahead right now and increase our type 1 error rate to 0.10. So instead of the usual 0.05, let's double it to 0.10. If you leave all the other input parameters the same and click calculate, you'll get a graph that looks a little bit like this, and you'll see that of course sample size has stayed the same. We haven't done anything with that. The effect size has stayed the same. You can kind of see the distance between the two sampling distributions is the same. That we haven't changed anything about that. Because we have changed the type 1 error rate, specifically we've made it bigger, we now have a different critical value. Because now, instead of dividing the null sampling distribution into a 95% region and a 5% region, we're dividing it into a 90% region and a 10% region. So you can see that red shaded region now is twice as big as it was before. The the critical value for the test statistic has decreased, which in a sense makes it easier for us to reject the null hypothesis. So for instance, we might have an observed t-statistic in our sample of data that was 1.5. Now the previous critical value of 1.86, I think it was, that's not big enough, or that is not a large enough t-statistic to reject the null hypothesis. If we change the type 1 error rate, making it bigger, accepting a greater possibility of false positive errors, then we could reject the null hypothesis using a t-statistic of that value. We made it kind of easier for ourselves. And again, you can see that that red shaded region is relatively large. What you can maybe also see, although admittedly this is a little bit subtle, is that the region shaded in blue in the alternate distribution is now a little bit smaller. Instead of being about 0.91, it's now 0.84. So the type 2 error rate has decreased as a function of increasing the type 1 error rate. And again, because power is 1 minus the type 2 error rate, we've actually increased the power from about 0.09 or whatever it was before to 0.16. Still pretty low power, but an improvement nonetheless. So to kind of summarizing this, increasing the type 1 error rate, increasing alpha, while keeping the sample size and the effect size constant, is going to decrease our type 2 error rate. So we're going to have less chance of incorrectly accepting the null hypothesis. We're going to have fewer false negatives. And we're going to have increased power, more chance of correctly rejecting the null hypothesis. This sounds good, of course, but increasing the type 1 error rate involves or introduces a greater chance of incorrectly rejecting the null hypothesis, a greater likelihood of false positives. So the important idea here is that increasing the type 1 error rate makes it easier to detect effects. That is, we get more power, but this improvement in power comes at a cost, a rather steep cost, I think most of us would think. Increasing type 1 error rate, a greater chance of incorrectly rejecting the null hypothesis. So this may leave you wondering, when does it make sense to increase the type 1 error rate in an effort to get more power? Well, it might make sense when maximizing power is really, really important. You know, if you're doing exploratory research, if you're, quote, just looking to see if a design or a method maybe works, if you're willing to accept that your type 1 error rate is getting bigger and that your apparently significant effect that you've observed in your sample might just be, well, it can always be a false positive, but the likelihood of it being a false positive is greater than what we usually use in statistics and psychology at 0.05, then maybe this makes sense. Maybe there's a situation where a false positive is not that big a deal for you, because based on your overarching kind of program of research, you're going to go back and replicate the study with a bigger sample of people from the same population. So having a false positive would be a bit of a setback. You might do a replication study and find out, oh gee, it's not there. Probably it was a false positive the first time. But if that's not a big cost to you, if gathering data is relatively expensive and quick, maybe you're using online surveys or something like that, then by all means fiddle with your type 1 error rate in an effort to get a little bit more power. Okay, so we're still on this quest. We're trying to increase the power in our analyses. We have some options for doing that. We could first reduce measurement error, talked about that already. We could increase the type 1 error rate, just talked about that a couple seconds ago. And our third option is to increase the effect size, and that will help us try to get more power in our analysis. So let's go back to G-power, and I want to leave things mostly the way they were before, but I want to make two important changes. First, I want to decrease the type 1 error rate back to 0.05, because I want to put that back down to a level which is more traditional for psychology and many other behavioral sciences. Then I want to take the effect size, which was 0.02, that's what we used in our previous example, a small effect, 0.02 Cohen's d, and I want to move it up to 0.05, which is roughly corresponds like a medium effect size. Leaving everything else the same, I'm going to go ahead and hit calculate. Okay, so we get some output from G-power. Much of this stuff is the same as it was before. So again, there is a small sample, 10 people, that stays the same. Our critical value for our test statistic stays the same, or rather, I guess it goes back to 1.86, which is what it was in our original kind of run through with G-power. That's because we're trying to leave our type 1 error rate back at 0.05, the traditional value, like I've said a few times now. Our effect size now is a little bit bigger, and this may not be really obvious unless you kind of squint your eyes and look at those two distributions, but there's a little bit more space between them, or they're separated a little bit more. They overlap a little bit less, because now the difference between them corresponds to a kind of a medium effect in psychology rather than a small effect, which is what we saw before. So what this gives us, or what a consequence of this, is that because that critical value and the green line that kind of highlights it stays the same, but the sampling distribution for the alternate hypothesis shifts kind of behind it, there's now less space or less blue shading to the left of that critical value than there was before. So instead of being, I think it was 0.91, it's now 0.82. So there's a little bit of a decrease in our type 2 error rate as a consequence of increasing our effect size. As we've said a bunch of times now, because power is 1 minus type 2 error rate, we've actually increased our power from 0.09, which is what it was way back before, to 0.18. So we've doubled our power by increasing our effect size. To be clear, we still don't have a ton of power, but that's an improvement, and that's probably something we'd be happy to observe if we did a post hoc power analysis like this. So just to kind of summarize it, if we increase our effect size, essentially bigger effects are easier to detect. So for a given sample size and level of type 1 error rate, if we increase our effect size, we get more power. If we decrease our effect size, we get less power. Increasing effect size while keeping sample size and type 1 error rate constant decreases the type 2 error rate, so we have less chance of incorrectly accepting a null hypothesis. We have fewer false negatives, and again, because of the relationship between type 2 error rate and power, we have more power. We have more chance of correctly rejecting the null hypothesis. So this probably sounds pretty good to you, and you may be wondering, how do I get a bigger effect size? Well, we could get a bigger effect size by having a better research design. So in the sense of an experiment, having better manipulation. So I'm using this example of alcohol being given to people in one group and not to people in the other group, and then we're measuring fear response with the eye blink component of the startle reflex. We could have a better manipulation if, instead of giving the people in the alcohol group a rather small amount of alcohol, we gave them a rather large amount of alcohol. So instead of getting a little bit drunk, they got really, really drunk. That would be, I think most of us can imagine, a better, or at least a stronger manipulation. It would be easier to detect any difference between drunkenness and sobriety if drunkenness is rather extreme drunkenness rather than mild drunkenness. We could also potentially get a better effect or a bigger effect size by having more sensitive measures. So if you've spent any amount of time around psychophysiological measurement, you know that there are all sorts of ways that you can fiddle with the software and the hardware to get more sensitive recordings of eye blinks, brain waves, muscle tone, whatever else. So let's imagine that we talk with the producers of our psychophysiological equipment, or work with an engineer to get a faster sampling rate or a better range of response detection or something like that. So we're measuring more precisely what even minor shifts in eye blink startle could be. We could detect bigger differences between the group that gets alcohol, however much they get, and the group that does not get alcohol. We'd have more sensitive measures. Kind of the important idea here, again, I've already said this, but it's worth repeating, is that increasing the effect size makes it easier to detect effects. Big effects are easier to detect than small effects, and hopefully we can all kind of understand that on a sort of an intuitive level. Increasing the effect size makes it easier to detect effects. Put another way, it just gives us more power. This is essentially the same thing as reducing error. I mean, the thing we're detecting, we're observing in our study, the variation in our outcome variable, is some combination of real effect and measurement error. And so by reducing measurement error, by increasing effect, pushing that line back and forward, we're doing essentially the same thing. Better research design methods capture more of what we want, the effect, and less of what we don't want, the error. Okay, so to keep on going with this, we're looking for ways to increase power. We've talked a little bit about reducing measurement error. We've talked a little bit about increasing type 1 error rate. Talked a little bit about increasing effect size, which is kind of the same thing as reducing measurement error. Let's go to the one that I think most students, and most faculty for that matter, think of when you ask how do you increase power, and that is increasing the sample size. So first off, let's go back to our GPower kind of workspace here and make a few changes. Let's well, it's not really change, but let's keep type 1 error rate at 0.05. Let's decrease the effect size back to 0.2 because of course previously we bumped it up to 0.5. Let's put it back to 0.2. Imagining again we have a small effect. And let's now double our sample size. Let's increase, instead of having 5 people in each group, let's make it 10 people in each group. So to be clear, the only thing now we've changed from way back when we first started was we've increased the sample size. Okay, so once you hit calculate, you'll get some graphical output that looks a little bit like this. And just to repeat really quickly, the effect size that we're looking at here that we've observed is a small effect size, and you can kind of see that in the sense that the sampling distribution for the null hypothesis and the alternate hypothesis are pretty closely located. They're almost overlapping. By increasing the sample size, we've had an interesting effect on the critical value for our test statistic. It was 1.86, and now it's dropped down to about 1.73. So in a sense, it's decreased, or it's moved to the left. Now recall that that critical value is just the value that allows us to divide the sampling distribution under the null hypothesis into the 95% cumulative probability region and the 5% cumulative probability region. But that number has changed. Why is that? Well, the reason why that happens is by increasing the sample size, we've actually changed, albeit somewhat subtly in this example, the shape of the curve of the sampling distributions under the null and alternate hypothesis. The curves kind of shrunk in and lifted up in the center. And the consequence of this is that that region to the left of the critical value in the alternate distribution has got a little bit smaller. Now, not very much smaller, because if you think back, or if you look back, you'll recall that that region, the type 2 error rate, is, or was, 0.91. Now it's 0.89. And because power is 1 minus type 2 error rate, our power has gone up from 0.09 to 0.11. We've had an increase in power as a consequence of doubling our sample size, albeit not a very big increase in power. Increasing sample size changes the shape of the sampling distribution for the test statistic, and that affects the probability of a given value for a given effect size and level, type 2 level of type 1 error. If we increase the sample size, we get more power. If we decrease the sample size, we get less power. It may be a little bit difficult to visualize this in my previous example, so what I've done here is try to run the same analysis with different numbers of participants. So here's the original with 5 people in each group. This is just, I'm assuming no effect here, so that the sampling distribution for the null and the alternate are perfectly superimposed. Here's our attempt to double the sample size to make it 20, doubling it again to 40. If you really squint, you can see that the shape of the distribution is changing a little, but what is more obvious is that that critical value for the type 1 error rate of 0.05 is dropping with each time that we increase our sample size. So as sample size goes up, the critical value gets smaller, and because of that, the test gets more powerful. To kind of summarize that point, increasing sample size while keeping type 1 error rate and effect size constant decreases the type 2 error rate, so we have less chance of incorrectly accepting the null hypothesis, we have fewer false negatives, we have more power, we have more chance of correctly rejecting the null hypothesis. So the important idea here is increasing sample size makes it easier to detect effects. It increases our power. But the increase is not as big as you might think. For instance, in this example, we doubled the sample size and we got a power increase of about 3%. So our power went up from about 8 or 9% to about 10 or 11% by doubling our sample size. That's not a lot. And I'm not trying to pick on people here, but I think it's often said, oh, you should increase your power, you should increase your sample size, and what people maybe imagine is that, well, I'll just gather 5-10 more participants, that'll give me more power. It will, but probably not as much more power as you think. So increasing sample size will increase power, although it might not increase it as much as we might like or as much as we might hope. But what if we really go all in on this approach? What if we recruit a really large sample for our study? This is sometimes done in situations where we can gather data online, perhaps using Mechanical Turk or Qualtrics or some other system that allows us to get hundreds or even thousands of participants to answer our questions for a relatively little amount of time or money in terms of our research. This is not a bad thing to do, but it can create a situation in which we have what's sometimes called an overpowered study. A study in which very small effects, very small differences between groups or correlations between variables can be statistically significant. Again, that's not bad, but it can be problematic if those effects, which are very small, correspond to sort of trivial differences or relationships in the real world. An example that I'm thinking of here is, it seems like every few years somebody publishes a study that looks at the relationship between like social media use and levels of personality variables, especially narcissism. When these studies are published, they often make a bit of a splash in the science journalism sources like blogs or the science section of major newspapers, because I think they tend to confirm probably rather prejudiced attitudes we have about people who use Facebook or use Twitter. Like, oh, everyone's so narcissistic, they're always taking selfies, etc., etc. I haven't looked really recently, but the last time I read into this literature, it seemed like many of these studies used really large samples of people, because it's relatively easy to gather large amounts of data on people's social media use. You can even put the questions on social media. And in these large samples, it's sometimes observed that there's a small correlation between someone's level of narcissism and how much time they spend on Facebook, or someone's level of narcissism and how many selfies they take in a given week, or so on. Now, maybe that's interesting, but I think it's often not very interesting, because those small correlations or those tiny differences between men and women or young people and old people can be statistically significant in a really huge sample, even if in practical terms they don't really mean that much. If the amount of variance in the outcome variable narcissism, let's say, is only very small or overlaps only very slightly with the amount of variance in the predictor variable, use of the internet, use of Twitter, or so on. I don't mean to be overly critical of this line of research, but it just strikes me as an example of overpowering studies and then kind of over-interpreting the results. So throughout this lecture, I've talked about a few different approaches that you could take to increase the power of the analyses that you might do with a rather simple independent experimental design. You can see that some of these approaches will tend to increase power. I mean, I guess they all will, although in some cases the increase is not quite as much as you might think or you might hope. What if we tried to combine some different methods in one go? Let's specifically try to increase the effect size, aka reduce measurement error, and increase the sample size. Specifically, I'm deciding not to fiddle with the type 1 error rate because I am imagining that that's a hard sell from the perspective of trying to get your research published. So we're leaving type 1 error rate alone, but we are increasing effect size, decreasing measurement error, and increasing sample size. Okay, so let's go back to G-power, and let's keep the type 1 error rate at 0.05. Let's increase the effect size to 0.5, so we're imagining that we could replicate the study, except this time use more sensitive measures or more effective manipulation, maybe get people rather drunk in our alcohol dose group. And then we're doubling our sample size again to now be 20 people per group rather than the original 5 people per group. If you enter all those input parameters and hit calculate, you'll get some output that looks a little bit like this. We've combined different methods. Our type 1 error rate has stayed the same as it was before, but by increasing our sample size, we've changed the shape of the curves for our sampling distributions, although, again, it's a bit hard to see that unless you really look closely. The effect size has increased, and you can see here this bigger gap between what we consider, than we saw with a small effect, that bigger gap between the location of the sampling distribution under the null hypothesis and the sampling distribution under the alternate hypothesis. Our test statistic is smaller. It's dropped relative to what it was way back in the beginning when it was 1.86. It's now 1.69. And again, that's just the value that we use to divide the sampling distribution under the null hypothesis into the 95% region and the 5% region. So that value's dropped a little bit. And the critical value divides the sampling distribution under the null. It also divides the sampling distribution under the alternate hypothesis, our dotted blue distribution kind of in the back there. The area to the left of that line defined by the critical value is our type 2 error rate. If our test statistic falls below the critical value, let's say it's 1.5, we don't reject the null hypothesis. But if in fact there really was a difference between groups in the population, we would have made a false negative or a type 2 error. So that rate drops a little bit as our effect size gets bigger and our sample size gets bigger. And because type 2 error rate drops, power goes up. It goes up to about 0.46. So we've got almost 50% power at this point by combining two methods. The important idea here is that increasing power is not easy. In this example, we quadrupled from the original the sample size, and we somehow managed to get a medium effect size. We're sort of imagining we had better methods or better manipulations. And the power went up to a little less than 50%, which means that even with our new and improved version of our study, we still have kind of less than a coin flip's chance of detecting an effect if one is really there. Perhaps the real important idea here is that research in psychology is difficult, and I hope throughout this lecture I haven't come across like too much of a critic or a crank. The reality is that this little example that I've given is based loosely on the study that I did for my master's thesis, a study which took me well over 2 years to complete in terms of the amount of fiddling I had to do with it and the amount of people I had to recruit. It's hard to study in psychology. We typically need to recruit large samples, but because we're working with people most of the time, that's really hard to do because people have busy lives and they're not always inclined to volunteer for our studies, especially studies that take a long time to do or are difficult or challenging. It's funny, I can think back to talking with friends who are in neuroscience and study non-human animals, and for them it's relatively easy. If you need more rats for your study, just buy them, have them shipped to the lab. Not so easy when you're working with people. Moreover, when you're working with people, our measurement errors tend to be rather big. So the things that contribute to any of our dependent variables or our outcome variables are many. So how much fear response someone has, or how much self-control someone has, or how much someone feels depressed or happy or whatever on a given day is influenced by probably many variables. And it's hard to capture all of them. It's hard to control all of them either experimentally or methodologically or statistically. Our effect sizes tend to be rather small. The relationships between the predictor variable or variables that we care about and the outcome variable that we care about is often only a minor piece of the overall picture. We're studying the relationship between alcohol and fear response. Well, fear response is influenced by a lot of things, and however much alcohol has to do with fear response may be only a little piece of that puzzle. There just aren't a lot of simple predictor-outcome relationships in human behavior, meaning like one clear predictor, one clear outcome. Most relationships are influenced by many other variables. Anyway, with all that complaining aside, and hopefully it's good-natured complaining, here's something for you to try. And if you're doing this just watching me on YouTube, you don't even need data to do it. You can just download GPower for free and play along. Obviously, if you're enrolled in my class, open up GPower and play along. I want you to try to adjust analyses to increase power with the goal of having a type 1 error rate of 0.05, a type 2 error rate of 0.20, and consequently a power of 0.80. Those are Jacob Cohen's suggested levels. And fiddle with the input parameters on GPower to see how big a sample do you need to detect to have that level of power with a medium effect size or with a large effect size. I think you'll be surprised at the results you get. So at the risk of making a somewhat abrupt transition, I want to start talking about confidence intervals now. And really this will make sense because we're talking about making inferences based on sampling distributions for test statistics, so it does kind of connect to the previous discussion of power and power analysis and some of those related issues. And to transition us again, we're going back to talking about that counseling center example, which I've used in previous lectures. And so if you're enrolled in my class, you can find those data sets in either Excel or SPSS format on Blackboard. If not, you can probably pretty much follow along as we go. So here is that rather familiar at this point description or pictographic representation of what our study looks like. We're getting participants. We're hopefully randomly assigning them to either be in a treatment group that gets some sort of new therapy that we're offering at the counseling center, or a control group that's getting some other type of treatment, perhaps treatment as usual, or perhaps a wait list. In some way we're creating a counterfactual for them. And then down the line we're looking at the overall difference in functioning between those two groups so as to evaluate whether our new form of psychotherapy is any better than what we were previously or are currently doing. You can imagine we could do this one time. We could recruit a sample of people, assign them, follow them, etc. And we could compute some statistics like some sample means, or a test statistic like a t-statistic comparing those means, and so on. If we really wanted to, we could do the same study again. We could recruit a new sample of people, assign them, follow them, and so on and so on. So again, each time we run the study, we can compute some different statistics. For the time being, let's just focus on computing a mean level of functioning for the folks in the treatment group and the folks in the control group. Now, if we repeatedly ran studies again and again and again as the semesters rolled by, we'd eventually get a lot of different values for those means. Each of these means, each sample mean, is a parameter estimate. It is estimating a population mean, the population of all people who are in treatment, and the population of all people who are not in treatment. If we took the means for all the treatment means and grouped them together, we'd have a sampling distribution. If we took all the control means and grouped them together, we'd have a different sampling distribution. So again, these are called sampling distributions. They're just groups of values from statistics, in this case means, that are gathered together from repeated sampling. And the standard error of a sampling distribution is just the standard deviation of that distribution, how spread out or dispersed it is. We sometimes talk about the standard error of the mean. That's just the standard error of a sampling distribution of means. If you're having a hard time visualizing what this looks like, you may recall this image here. Here we have 3 different samples. Each time we're computing an average on some variable, who knows what. And you can see the distribution for data for each sample. It has its own shape, and there's some sort of a statistic we extract, like an average. If we take all those averages and put them together with many, many, many more over a very large or indeed infinite number of samples, we'd have a sampling distribution. Now, to be clear, we don't actually make sampling distributions when we do our research. We don't run our study thousands and thousands of times. This wouldn't be practical or probably even possible. However, as a little note here, there are some modern statistical techniques that use computers to simulate the data from thousands and thousands of samples and thereby create kind of a simulated sampling distribution. We don't do that right now, or at least we're not in this class. Maybe in the future I'll talk about it, but not for right now. For right now, we're going to fall back on the more familiar approach to hypothesis testing and to confidence intervals and similar types of things, which is we make assumptions about what the sampling distribution for our statistic would look like. And these assumptions are based on the central limit theorem that I've covered a little bit in previous lectures. So by way of a quick review, the central limit theorem just tells us that distributions of sums or averages of elements will approximate a normal distribution. In this context, elements really refers to errors that make individual values different from the true population value. Imagine that we are drawing samples from a population of folks, and that population is all people who are or will or could be in psychotherapy treatment. We're drawing samples from those, and we're computing the average level of psychological functioning among the people in each of those samples. In a sense, all the people in our sample should have the same value of psychological functioning, and that value should be the same as the population value for psychological functioning. That's not the case, and the reason it isn't the case are because of all the little things that make one person in our sample different from another. Perhaps that person has a slightly lower level of functioning even though they both went through the same psychotherapy, because that person has a slightly more severe case of depression. Or another person has a slightly higher level of functioning because that person happens to be slightly younger and hasn't suffered as many of life's cruel insults and so on. The point is, there are all sorts of little things that pull each individual person off of, in a sense, what their true value should be. However, we assume that those little things, those little elements, those little errors are independent of one another, and they are randomly and kind of evenly distributed among our sample and across the population. So the consequence of that is, if we are creating averages, those little things, or sums, those little elements should average or sum to 0, bringing us fairly close to what the true value of the population, true value in the population is for whatever it is we're measuring. For instance, if the true level of psychological functioning in the population is 50, let's say, then our averages for any samples we draw from that population should be mostly pretty close to 50. And if we make a sampling distribution of all those averages over many, many, many times, most of those, the center of that sampling distribution should be pretty close to 50 if we make these assumptions about the nature of these errors. And also, if those sums or those averages are drawn from large samples. So if our samples that we're drawing from the population are only 5 people each, then it's less likely, or it's less possible, that those little elements or errors can sum or average out to 0, whereas if we are drawing samples of 50 or 500 at a time, it's much easier for that to happen. To put this all in a slightly simpler language, this is just one of the reasons why large samples tend to be better than small samples. They tend to produce sampling distributions that are more narrow, that are less dispersed, and are more closely aligned with the true population value of the parameter that they're trying to estimate. So if this is all a little bit difficult to visualize, take a look at this picture here. And I think I might have used this before, but at this point in my recording, I kind of start to lose track. Anyway, imagine here what we have is that we have an actual defined population of data, like we've created in our computer, like in Excel or some other spreadsheeting or databasing system, a very large amount of data, and we know that the population mean for whatever this variable is exactly 4.5. What we're going to do first is draw 500 samples from that population, each of those samples containing 5 cases, and we're going to create a sampling distribution for the averages of each of those 5 cases. That distribution, that sampling distribution, is what we see over here towards the left. It sort of looks normal in its shape, sort of. And if we look at the mean of that sampling distribution, it's 4.64. Which is close to 4.5, of course, but not exactly on 4.5. Now imagine that we discard this set of analyses. All those people are sort of thrown back into the population. And now we're going to sample from that population again, this time drawing samples of 50 people and computing the average for whatever the variable is for those 50 folks. Putting all those averages together to make a sampling distribution 500 times, so we get quite a lot of samples. Now, that's what we see on the right. That's the sampling distribution we see on the right. You can see it's much narrower. It's less dispersed. The standard deviation, that is the standard error of that distribution, is less than half of what the one was from the previous distribution. And the the mean for the sampling distribution is lined up perfectly with the population mean. So hopefully this helps for you to visualize. The basic idea is when we are computing things like sums or averages, which to be clear we often are in psychology, if we can draw large samples from our population and if we can make assumptions about the nature of the errors that pull people away from what their scores on our variable should be, in a sense, those essentially assuming that those errors are random, then we can feel pretty comfortable with the idea that our sampling distribution, were we to make one, would have these attractive properties. It would be fairly narrow, it would be symmetrical and rather normal in shape, and it would be a good, unbiased, that is sort of correct indicator of the population parameter that we're interested in, the average or the sum in the population that we care about. So we're kind of building this idea based somewhat on mathematical theorem, the central limit theorem, and somewhat on assumptions, because historically we haven't had the ability to use modern computing techniques to simulate sampling distributions, and we certainly have never and probably never will have the time and resources to just conduct 500 studies in the same population just again and again, and at the very end of it build a sampling distribution out of the data we've actually collected. So what do we do with all this information? Well, we can extract a basic principle or idea. That is, if samples are large, and historically large samples in psychology have been thought of as maybe greater than 30 people or cases in each group, maybe that should be more like more than 50, then the sampling distribution we will assume based on the central limit theorem and some assumptions about errors will be normal in its shape, and its mean will be equal to the population mean, and its standard deviation, that is to say the standard error of the mean, will be equal to the standard deviation of our sample divided by the square root of our sample size. So we can know, or I guess make a good guess, we can't really precisely know what the population mean will be and what the standard error will be. Okay, now this is going to seem like an abrupt end, but frankly I had to call this lecture off at some point. We've been here over an hour and a half, and as you may remember from early on, I was complaining about having a cold. I'm getting over it, but it's not easy. Anyway, what did we learn so far? Well, we did a lot about power analysis, and I hope that part made the most sense to you. I hope you learned something there, and if you didn't, please take some time to go back, look at it again, and if necessary, ask me questions. We focused a lot on ways to increase power, taking a kind of a post hoc perspective, but the same principles would apply if we were doing an a priori power analysis. After that, I began to talk about confidence intervals a little bit for population means, but I didn't get too awful far because, again, I kind of gassed out. With that in mind, what's the preview for next time? Well, next time I'll pick it up and I'll talk a little bit about how we can use this information to create confidence intervals and error bars, and I'll begin talking about some of the biases and assumptions that go along with the type of analyses that we do. That'll be kind of like the last topic I touch on in Unit 1 of this class. Anyway, if you made it this far, thank you for your patience and your attention. It's not easy for me to record these sometimes, and I imagine it's not always easy for you to keep up and listen to all of it, but if you can, make yourself a cup of tea. That's probably what I'm going to do in a second here. Relax, think about what you've learned, and if you have any questions, please let me know. I'll be back with another lecture very soon. Bye-bye.